Welcome back to Power Series on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. In the previous video, we did an example of an integral in which we were forced to convert the function we're integrating into a power series representation, which ultimately comes from the Maclaurin series expansion. And sine x over x dx is not an integral that you can actually do using normal integration techniques from the previous chapters in Calculus 2. So we have to convert the function in the integral into a power series representation, which ultimately comes from the Maclaurin series expansion. And in this video, we're going to do an integral that is no different. Let's look at our integral. We're going to integrate the function e to the x squared dx. And again, this function e to the x squared, because there's no other term in which we can do a u substitution or anything like that, we're forced to convert e to the x squared power into a power series representation. But first, we're going to start with the base function on which e to the x squared is based on, okay, which is just e to the x. That's our simple function. And we actually derived the power series representation for e to the x in the previous video. We went through a bunch of Maclaurin series steps to ultimately determine that e to the x is exactly equal to the series from n equals 0 to infinity of x to the n divided by n factorial. All right. Now, remember how we deal with this. If we want to find the power series representation for e to the x squared, we imagine that whatever's in this parentheses here, this x squared, is what gets plugged into the x function in the power series representation. So, if we want the power series representation for e to the x squared, we take wherever the x was in the original power series and plug in x squared. So therefore, e to the x squared power as a power series is the series from n equals 0 to infinity of x squared to the n power divided by n factorial. And in fact, what we can do is, because we have x to a power, which is raised to another power, we can multiply the powers together. And so our function is the series from n equals 0 to infinity of x to the 2n power divided by n factorial. So now we have a power series representation for our function within the integral. Now we can actually compute the integral. So the integral of e to the x squared dx is equal to the integral of the power series from n equals 0 to infinity of x to the 2n over n factorial dx. Now again, something to keep in mind is that we're integrating only with respect to x. So we have two terms, so to speak, here. We have a numerator which is in terms of x, it's x to the 2n, and a denominator which is n factorial, which is not in terms of x. So we're not even going to mess with the factorial part at all, we're only dealing with the x part, and we can do a simple power rule integration. So we have x to the 2n power. If we want to integrate that with respect to x, we raise up the power of the exponent by 1 and then divide by that new power. So if we raise x to the 2n's power by 1, we get x to the 2n plus 1, and then we can divide by this new power, so we divide by the quantity 2n plus 1. And this series from n equals 0 to infinity of x to the 2n plus 1 divided by the quantity 2n plus 1 times n factorial, along with our plus c, our constant, that is the integral of e to the x squared dx. Now again, this constant, remember, you can't have added at the end. Some people might like the c at the front just because when it's at the front it explicitly tells you that the constant is not within the series. Although if you put plus c at the end, it would still be correct technically. Okay, so this is how you compute an integral when you're forced to convert the function within it into a power series representation. All right, so hopefully this video gave you a little bit of intuition on that. Please make sure to like this video and subscribe to the channel for future videos and notifications. And then in the next video, we'll do one more example of this, and then we'll do some derivative examples of power series representations. Thank you.